let's consider this example we ended with last time. We got this function. What was this function right there? First of all, it is for a forced harmonic oscillator that's undamped. So P is 0. The differential equation, the left-hand side is just that. There's no y prime term. Okay. Again, eliminating the friction is pretty much impossible, but so this is sort of idealized. Maybe it's fairly accurate when the friction is really small. And it's an interesting thing to think about, but it is a forced thing, and we have the right-hand side function be cosine of, what's that? Omega. Cosine of omega t, not cosine wt. Again, I won't get mad if you say w, but you really should say omega. What did we find from this? We found the solution of the corresponding homogeneous equation, the unforced equation, sometimes called the natural response. This was the general solution of that. There's no omega there because the right-hand side is 0 for the corresponding homogeneous equation. Square root of q is the coefficient of t for that. We complexified the equation. We took this equation and made the right-hand side be a complex exponential, whose real part is that, by Euler's formula. Why do we do that? Well, for one thing, it makes guessing a solution a bit easier, because you can guess just one exponential instead of 2 trig functions. Guess yc equals some undetermined coefficient a times e to the I omega t. And what did we find? We found that a was 1 over q minus omega squared, as long as we're not in the case where we're not dividing by 0. As long as we're not in the case where we're dividing by 0. Q is not equal to omega squared. Thought of another way, omega is not square root of q. We do think of omega typically as positive, so I won't say plus or minus square root of q. The parameters p, q, omega are typically thought of as being positive. P and q for sure, and typically even for omega. All right, and then what do we go from there? What do we do from there? Well, we got a yp from yc to be the real part of yc. Why the real part? Because the right-hand side of the non-homogeneous forced equation is a cosine. If it had been a sine, we'd take the imaginary part. I'm focusing on the cosine case because we're going to see that's a little easier to think about. I will probably mention the sine case on Friday, but we're focused on the cosine case for the right-hand side. In other words, the real part of a times e to the I omega t, and in this undamped case, a is a real number. We're going to see when you have damping, a ends up being a complex number. Here in a few minutes, we'll see that. But a in the undamped case is a real number. Think about Euler's formula there, cos omega t plus I sine omega t. The real part of this is going to be a cos omega t. Make that more like an omega. Where a, again, is 1 over q minus omega squared. So that is yp. That's a particular solution, one particular solution of this forced equation. And then what do we do? We solved an initial value problem. So I'm just summarizing what we did at the end of class last time. Class, what was it, 26, today's class 27. We solved the initial value problem where both the initial position and initial velocity are 0. The mass is sitting at the equilibrium point position and not moving. When we start to tip the table, say, we apply a forcing function. It doesn't stay with 0 initial conditions because of that forcing function. If we didn't have the forcing function, then it would stay there. It would move, it would stay at the equilibrium position. But we have the external forcing function, so these conditions do not imply a stationary mass. The mass moves back and forth. When we use those, we found K1 and K2. We found K2 to be 0, and we found K1 to be actually the opposite of A. And now come over to the Mathematica. That means this function that's highlighted here, that is why the unique solution of the initial value problem. That's what it equals. Because K1 was -1/q minus omega squared, that's where that negative sign comes from. And K2 was 0, so there's no sign term in here at all. Just a nice simple special case, a nice simple initial value problem, and a relatively simple solution. However, its graph is not relatively simple. It's pretty wild looking, for at least for certain values of omega and q. So here we have a graph of what the unique solution of the initial value problem looks like when q is 9 and omega is 1. Kind of interesting. What would the motion be like? This is the y. Kind of an interesting motion, I guess. It would be a small amplitude motion that I guess moves to the, if the right is positive direction and the left is negative, moves to the right a little bit before coming back negative, staying negative but getting close to the equilibrium at 0, y equals 0, before going negative again, then going positive, going back to equilibrium, staying positive. It's a pretty interesting motion. I'm getting it right with my hand here. Something like that. It's not a pure sinusoidal kind of oscillation. But it becomes even more interesting as omega gets closer to square root of q. I don't want omega to equal square root of q, but as it gets closer and closer to square root of q, the graph, the unique solution gets more and more interesting. We started getting features looking like this, where you've got oscillations within oscillations. And the amplitude can get really big too. And we want to avoid the omega equals 3 case here. Oscillations with oscillations. There's a fast oscillation, like that, that gets bigger and bigger in amplitude, and then smaller and smaller, etc. So there's sort of a slow oscillation too. You can think of that slow oscillation as sort of enveloped within two graphs. A graph that would go like this, and another graph that would go like this. It's like it's in an envelope of those two kinds of graphs. What I'm about to do is I'd like to figure out, I'd like to use complex numbers in the way that I did at the end of class last time, to try to figure out what the period and frequency of the fast and slow oscillations are. I'm not going to show you every detail. Let's just summarize what we did, again, still at the end of class last time. Again, this function is 1 over q minus omega squared. I lost the formula just to look at it. In parentheses, cos omega t minus cos square root of qt. And we went back to using complex numbers again, the complex exponential. You actually can do what I'm doing here without doing that. You can use trigonometric identities if you want. Probably would be something you wouldn't remember, so you'd have to look it up though. If you learn this technique pretty well, you don't have to look up trigonometric identities. In a sense, you can rederive them as needed. It's kind of fun. There's other good reasons for it as well. Recognize that this is the real part of the difference of two complex exponentials that look like this. The real part of that by Euler's formula. And then do this trick, which is a pretty handy trick. let alpha equal omega plus square root of q over 2, and beta be omega minus square root of q over 2. Seems kind of mysterious. Why do that? Well, because these are chosen so that alpha plus beta equals omega, and alpha minus beta equals square root of q. In effect, to derive these equations, you'd solve that system for alpha and beta, thinking of omega and q as fixed. That would get you to these equations, but you can also see once you've defined these, that these two things are true. You can see that pretty quickly by adding and subtracting these. And that's handy because that allows us to rewrite this expression here, this thing inside the real symbol, as e to the I alpha t, e to the I beta t, minus e to the I alpha t, e to the negative I beta t. Because, why? Because you replace the omega with alpha plus beta, and you replace the square root of q with alpha minus beta. And that's nice because you've got a common factor of e to the I alpha t that can be factored out. And what's left over, e to the I beta t and e to the negative I beta t simplifies to 2 sine beta t with an I. 2i sine beta t. Now, I haven't shown that to you here. That would be for you to work out. I claim that e to the I beta t minus e to the negative I beta t, I claim that equals 2i sine beta t. You should work this out yourself using Euler's formula, and also using the fact that the cosine function is an even function and the sine function is an odd function. Those are the 3 things you need to verify this. Meaning cosine of negative beta t is the same as cosine of beta t. And the cosines end up canceling. Sine negative beta t is the opposite of sine of beta t. Sine negative beta t is the opposite of sine of beta t. That's reflecting the fact that sine is an odd function. So you need those facts. I would encourage you to try that on your own. Make that replacement. I forgot my real part here. Still need my RE. Think about that as cos alpha t plus I cos beta t. What's the real part of this going to be? Doing that in my head. The real part is going to come from multiplying this times the imaginary part of that so that you get an I squared. And that means you're going to get a negative sign, technically. I haven't made a mistake. Looks like the real part of this is going to be negative 2 sine alpha t sine beta t. I think that's right. You're going to get a sign in both spots because the imaginary part of this right here is sine beta t. It's I times sine beta t. Sine beta t is the imaginary part. And sine alpha t. Multiply those, you'll get a sine alpha t and a sine beta t. You'll get the 2 there, you'll get an I squared, that's negative 1. What's the reason we're doing all this? We're almost done. Again, the reason we're doing is we want to understand that beating phenomenon, fast oscillations within slow oscillations. going back and replacing alpha with omega plus square root of q over 2 and beta with omega minus square root of q over 2. So many back and forth replacements it seems like here. Allows us to write this unique solution of the initial value problem as negative 2 over q minus omega squared sine alpha t, alpha is omega plus square root of q over 2, times sine beta t, beta is omega minus square root of q over 2. Now you think about this here. You got this constant times the product of two things that are always, each thing individually is always between negative 1 and 1. If omega is really close to square root of q, if omega is approximately square root of q, not equal to it, because that's the case we haven't thought about, that means omega minus square root of q over 2 is close to 0. And omega plus square root of q over 2 is not so close to 0. Or should I say that is relatively large, where by relatively large, it still could be a small number. It still could be 1 or something. It doesn't have to be a million or something. It's relatively large compared to that one. Using vague terms here. So think about each of these signs individually. If omega is close to square root of q, so that this coefficient of t is close to 0, that's going to correspond to a small frequency, a slow wave oscillation, large period. And this is relatively large, that's faster frequency, higher frequency, oscillating faster, smaller period. The fast oscillation has period 2 pi divided by this, which is really going to be 4 pi divided by omega plus square root of q. And the frequency, that's 1 over that, omega plus square root of q over 4 pi. Would be in hertz if timed in seconds. And the slow oscillation the period is going to be 2 pi over that. Now that could be a negative number even though omega and q are positive. So technically speaking, you should use absolute value signs. 4 pi over the absolute value over omega minus square root of q. And the frequency is going to be the reciprocal of that. Frequency is small here in this case. The period is large for the slow oscillation. Let's see if these formulas match the graph that we see. You might want to get your calculator out. So I picked here, Q is 9, omega is 2.86. Let's think about the fast oscillation. Let's think about its period here. I'd have to go 4 pi divided by the sum of these two things. Actually, the square root of Q, excuse me, which is 3. So take, for example, you could do 2.86 plus 3 to get 5.86. Then take 4 pi divided by that. 4 pi divided by 5.86 gives you a period of about 2, a little bit bigger than 2 for the fast oscillation. On the scale, does that seem about right? Think about the horizontal peak-to-peak distance here. Is it 2? Well, there's a 20. There's 10. 5. Yeah, looks reasonable. This peak is close to 5. This peak is close to 2.5 to 3. Seems reasonable that these peaks are about a little more than 2 units apart horizontally. That is corresponding to the fast oscillation. How about the slow oscillation? What's its period? Now do omega minus square root of q, 2.86 minus 3. Take its absolute value, you'll get positive 0.14. Take 4 pi divided by 0.14. You get a pretty big number. You get about 90. Is that the period of the slow oscillation? Don't think peak to peak here. Think peak to peak with the one that's off the screen. Think about starting here and going through one full cycle to there, and we are close to 90. Okay? So the point in doing all this mixture of trigonometry with exponentials is to help us understand why you're observing the beating phenomenon. This form of the solution is more helpful in understanding that graph than this form is. That's the point. That's the whole point. All right, now let's add in some damping. I'm going to continue doing the general abstract case. You will continue to think about particular numbers on your homework. Particular P, Q, and omega. I do want you to be able to handle the abstract kind of case, though. I might put a question or two related to it on the test. So this is worth doing. I think it's definitely a good skill to be able to handle these general cases. Now we're adding some damping. We have a P in there that's positive. We will continue to have a right sign that's just a cosine omega t, keeping things as simple as possible. You could modify it. You could make a sine omega t on the right. You could have an amplitude other than 1 there on the right. You could even do a linear combination of cosines and sines. We want to try to keep it as simple as possible because it's already kind of difficult to deal with here. I'm not going to bother writing the YH. What would you get for the YH? You'd end up either in a complex eigenvalue case or not. You might get oscillation for YH. If you have complex eigenvalues, you would. You might not. If you have real eigenvalues, you would not have oscillations for YH. Just pure exponential decays. I'm talking about the corresponding homogeneous equation where 0 is on the right-hand side. I'm not going to bother writing that down. Okay? We're going to focus on YC and YP. Complexify. Excuse me. Complexify. Another benefit of complexification that I think I have not mentioned is that because when we have a cosine on the right-hand side of the original equation, we take the real part of YC to get YP, and we take the imaginary part of YC if we have a sign on the right-hand side here. In effect, you're getting, by doing the complexification, in effect, you're solving two problems at once. So that's another benefit of it. Complexify. Guess YC equals A e to the I omega t. It's going to be more complicated now. Because P is greater than 0, you're going to have to think about including the first derivative of this in there. Differentiate. The first derivative is going to be A I omega e to the I omega t. By the chain rule, I omega is the constant. Get an extra factor of it there. Differentiate again, you get another factor of I times omega, meaning you get an I squared times omega squared. I squared is -1. So this becomes negative A omega squared e to the I omega t. Because you get an I squared. Plug that into the left-hand side, set it equal to the right-hand side. left-hand side becomes yc double prime plus pyc prime plus qyc. That will be, better be careful here, negative a omega squared e to the I omega t plus p a I omega e to the I omega t. It's almost like we're spelling a word here. Huh? Hey, we. No. Plus q a e to the I omega t. Right? Look good? No mistakes? Group together the two terms that involve, well, that don't involve an I. Also factor out the common factor of a e to the I omega t. That's in every term. What's left over? The parts that don't involve an I are the first and last terms, which gives you a negative omega squared there and the q left over there. And the terms that do involve an I, it's just one term, it's this one. It's being multiplied by whatever's left over, p times omega. Set this equal to e to the I omega t. You want those to be equal for all t. Therefore, this entire thing right here must equal 1. So a must therefore be 1 divided by this thing. A equals 1 divided by q minus omega squared plus I times p times omega. That's now a complex number. To write it in the standard form, something plus something times I, you'd have to do the trick of multiplying the top and the bottom by the complex conjugate of the bottom. In other words, multiply question.
Why is q minus omega squared?
It's not. Thanks. You didn't see that. It's gone. Actually, I think my brain was thinking of something else where I do square that, finding the length of A as a distance to the origin, but for the moment we're not doing that. Well, actually, we're about to do that, because now when I multiply by the complex conjugate, on the top I get q minus omega squared minus I p omega. And on the bottom, when I multiply the bottom by that, it's like magic, the imaginary parts cancel. The things that are being multiplied times I when you do FOIL, first, outside, inside, last. First times first is q minus omega squared squared. There, that's not a typo. Outside times outside, think with me here, is this thing times that thing, giving you negative I p omega times that. Inside times inside is this thing times this thing, giving you positive I p omega times that. And those end up canceling. When you multiply a complex number times its complex conjugate, you get a real number. That's the benefit of doing this. Now done here, I also get last times last, I p omega times negative I p omega, giving you negative I squared p squared omega squared. Negative I squared is positive 1. Not only do you get a real number, you get a non-negative real number here. All right? Yikes, kind of nasty looking. That is evidently what we need to multiply e to the I omega t by to get yc. And then what would I have to do to find yp? I'd have to find the real part of that, which means I need to multiply this crazy thing by cos omega t plus I sine omega t. Yikes. Well, it's not so bad. Let me just write the answer. Yp because again the right hand side is a cosine, is going to be the real part of yc, the real part of a e to the I omega t, where a is that. And that will be, think carefully, the real part of this is going to be what I'm circling here. That times the real part of this one will be real. Part of the real part of the answer. Part of the answer. It's going to be that one I circled times cos omega t. Q minus omega squared, I guess I'm going to use parentheses here, over Q minus omega squared squared plus P squared omega squared cos omega t. But there's going to be another term, a sine term, that's going to come from taking the imaginary part times I, it includes a negative sign there, times sine, times I sine omega t. The R squareds give you a -1, but the negative sign here makes it a +1. You're going to get P omega divided by Q minus omega squared squared plus P squared omega squared sine omega t. That is yp in this general case. For your specific problems, for the most part, you'll have specific numbers. You'll do the same idea, but the answer will look simpler at the end. You do typically have fractional coefficients for the cosine and sine. What we want to do for the rest of class today, however, 10 minutes or so, is we would like to write this in a way that's more understandable. Not so easy to understand that in terms of what it, trying to predict what its graph looks like, for example, without technology. I would like to write this and put an equal sign with the words would like. There will be maybe a question about whether it's possible or not to write this. We would like to write as capital A times cosine of omega t plus some number that our book calls phi. We'd like to do this. We might wonder, is it possible? If I had more time, I'd use Mathematica to graph this thing in a manipulate where I change p, q, and omega. What you would see if I did that, if I graph this thing, is you would see a sinusoidal wave, meaning a periodic wave of a certain amplitude in a certain period, possibly with some horizontal shift to it. Before I put this on the Moodle, I'll do that. I'll put it in there. For the sake of time, I'm not going to do that. You would see a sinusoidal wave. You would see that it looks like it's probably going to be possible to do this. And the answer is, yes, it is possible. Also, for the sake of time, I think I'm just going to tell you the answers for capital A and phi, actually. What are capital A and what are phi? Instead of trying to derive them, that's probably going to take too long. The book does the derivation, and surprise, surprise, they use complex exponentials again to derive capital A and phi. That shouldn't be a surprise by now. What do they find? They find that A is equal to the distance between little a and the origin in what's called the complex plane. I've had you read about complex planes in the back of the book in the appendix. I don't know that I remember if I've mentioned the complex plane before. It's a plane with axes on it. One axis you label the real axis, one you call the imaginary. But the imaginary axis is there, I drew it. It's there. It's just the labeling. Any complex number can be thought of as being a point in this plane. For example, the complex number 3 minus 2i can be represented in the point as a point in this plane by going along the real axis 3 units to the right of 0 and going along the imaginary axis 2 units down. That point right there can be imagined to represent that complex number. As a point in such a plane, this complex number has a certain distance to the origin. And just like absolute value of a real number measures that distance between that real number and the origin on a real number line, we also write, if you will, the absolute value of the complex number little a to represent that distance. Actually, the more official name for this is it's called a modulus of a. I think they want to emphasize that a is a complex number. That's why they invented a new word. Modulus of a. I won't get mad if you say absolute value of a, though. And actually, I think Mathematica does modulus with ABS, as if it's an absolute value in the regular sense. It also makes an angle. What should I call the angle? How about phi? With the positive real axis. In this case, you can think of that as a negative angle. You also could measure it in other ways. You could measure it around that way and think of it as a positive angle. And you could add 2 pi to your answers. Multiples of 2 pi, integer multiples. That angle is called an argument of the complex number little a, but I probably won't use that word again. I'm not guaranteeing it, but probably at least one more time. It's called the argument of the complex number. Just think of it as the angle. So little a, or capital A, the amplitude we're going to get is the same as the modulus or absolute value of a, and the phi can be taken to be the angle that I've drawn down there, which you can typically find with the arctangent function, though you have to be careful when you find it with the arctangent function. You have to realize that the ordinary arctangent function you usually think about with your calculator only gives you outputs between negative pi over 2 and positive pi over 2. The angle must be in the first or fourth quadrant. If it's in the second or third quadrant when you draw, you have to add pi to that arctangent output. If it's on the vertical axis, technically the arctangent is undefined, so you just look at the picture, okay? If you've got a purely imaginary number like 5i or something, it's, saying it again, argument, its angle is pi over 2. If it's negative 5i down here on the imaginary axis, then its argument is negative pi over 2. By the way, when I label this with a negative 2, I don't mean this number is negative 2. That number is negative 2i. It would be a purely imaginary number. I'm just saying on the axes themselves, and labeling that with a negative 2. So those are the answers. Well, though this one can certainly be simplified. What's the modulus of a? What's the absolute value of a? Find the length of that thing, which you find with the Pythagorean theorem. If I just call this alpha plus beta I, then you could write this as square root of alpha squared plus beta squared. All right, let's now write how alpha and beta depend on p, q, and omega. This will be square root. I'll get a common denominator right away. The common denominator is going to be that thing squared. The numerator is going to be that. I didn't have to do that. There's another way that I could have thought about that would have been quicker, because the bottom is the square of the top. Right? No mistakes? Therefore, I can cancel one of those factors and just write this ultimately as 1 divided by the square root of the bottom without a square there. I could have derived that more quickly based on something I erased, based on the fact that little a is 1 over q minus omega plus I p omega. And it turns out the modulus of a is the same as 1 over the modulus of this thing, and that modulus is going to be the square root. So that would have been a little quicker way to go. There's not really a formula for phi in a non-piecewise way, though Mathematica actually does have the capability of handling phi in a non-piecewise way. You can say that when the tangent is defined, tangent of phi is the imaginary part divided by the real part, the y-coordinate divided by the x-coordinate. And the q minus omega squared plus p squared omega squared, when you do that division, are going to cancel because they're both in the real and imaginary part. You're really just going to get a negative p omega over q minus omega squared. Actually, when p, q, and omega are all positive, we're going to typically think of this at least as being an angle in the 3rd or 4th quadrant. You'll see the book talks about that. Let's finish class by making one graph here. Okay. Let me just summarize what I'm going to do extra in the Mathematica. I'm going to graph these two functions. This function right here, and this function thought of as a function solved for phi. You can graph them in higher dimensional space if you can think of p, q, and omega as all being variables. But that would be, if they're all variables, that would be a graph you really couldn't imagine. It would be in 4-dimensional space. You can set, for example, p and q equal to constant and let omega vary and get a graph. You could set omega and p equal to constants and let q vary and get a graph. And you can also manipulate those graphs as those constants vary, meaning they're really parameters. And the goal in all of this is to understand the graph of, where to go, of yp as that sinusoid that I erased, a capital A times cosine omega t plus phi. How do p, q, and omega affect that graph? That's the goal. Okay. 5 seconds. The YH in such a context when t is greater than 0, as t goes to infinity, the YH goes to 0. And so the force response is ultimately, when you have damping, the main thing you observe. Okay? See you Friday.